Okay, thank you. Our next speaker is Dr. Thomas Van Dam. Tom is a principal at Nichols Consulting Engineers with over 35 years of civil engineering experience, specializing in pavement design, evaluation, forensic investigations, materials assessment, sustainability, and resiliency. Dr. Van Dam is an active member in ACI, where he serves as on the Technical Activities Committee, as well as numerous other technical committees. In total, Dr. Van Dam has published over 100 technical articles and is a frequent presenter on pavements, pavement materials, and sustainability. His presentation is titled Carbon Reduction Strategies for Concrete Airfield Pavements. Please welcome Tom Van Dam.
Awesome, thanks. And I see we're in Nashville. Actually, I'm in Nashville next week, but I did this presentation before I did the Nashville one, so I don't know how Nashville ended up here. Anyway, I'm going to talk about kind of what leads to some degree to the resiliency, need for resiliency that we just talked about, and then also some of the things that we can do right now, or we should be doing right now, to help mitigate the potential for climate change. And so a little bit of background, we've seen a little bit of it already, but you know, the changes in climate that are occurring are directly being linked to our activities as a species, right? The burning fossil fuels and some degree the making of Portland cement are contributing a lot of greenhouse gases into the atmosphere, and these are resulting in a warming of the planet with a lot of effects. So optimistic models, if you look at them, they're predicting substantial change over the next 80 years. And so a lot of people focus on 2100 and the changes that are going to occur by then. And you will also be aware, unless you're living under a bit of a rock, that most associations, industries are embracing a goal, right? You've heard of it, net zero by 2050, right? So the goal is to try to get this under control here over the next 30 years, which is not a lot of time. This is really important to look at this data, because this is data. This is not models. These are observed data showing as best they can, tracking back 2,000 years forward up into this little sliver from 1850 with the beginning of the Industrial Revolution to 2020. And so the chart on the left shows the long-term scale and this big blip that is unprecedented in reconstructed recorded history. And then if you look at the fluctuations on the right, this one's worth looking at in more detail. This is out of the International Panel on Climate Change report that came out last year. You can look at the actual measured, observed trends upward since 1950. And if you only look at the impacts of natural processes, volcanism, solar activity, it doesn't show up. So a lot of people try to attribute a lot of this to solar cycles and volcanism. If you take out the effect of the greenhouse gases we put in the atmosphere, it's flatlined. And so the evidence as scientists and engineers is very, very compelling. Predictions are, if like today we somehow went net zero, we would actually mitigate this effect pretty quickly, and we would see it happening. If we track optimistically, you're going to see that kind of middle SSP 2 to 4.5. And if we just keep doing what we're doing, we're looking at a 4 to 5 degree increase in average temperatures annually in the world. And this is significant. And, I live in the Upper Peninsula of Michigan. We're hoping for a little global warming up there. It was 10 degrees yesterday and snowing. So, but for the rest of you, especially Florida, where if the sea level goes up 3 feet, basically Orlando is almost becoming beachfront. And that's not a joke. That's actually true. It's going to be a serious problem. And so this is why we're doing this. It's actually serious. And as an industry, as an association, we are embracing this. We talk about sustainability in general. I'm not going to have really a lot of time to go through it, but the reason I put this up there is I'm going to be focused on our concrete materials today. That's a small little piece of the puzzle. Okay, we need to adopt life cycle thinking. We need to be thinking from the design, looking at optimized design, long life designs, how we're looking at our material processing. And that's where I'll focus on is everything I talked about today, our construction process, efficiency, possibly, calcium carbonate, mineralization, operations from a highway perspective is huge. Airports, not as much, but we definitely will want to think about how we're going to preserve things, keep them functional, deal with resiliency, and then in the end, the recycling of that material and then running it back through our new designs. And so all of this is important. The challenge in front of us, they're pretty great. And I will tell you, change is difficult, right, Tyler? People don't like to change, unless you're Tyler. Tyler likes to change every day, man. He's got energy. He embraces change. But most people freak out about change. But we have to start to embrace it a bit, understand this change is coming, educate ourselves, and then look at what we've done traditionally. Our traditional cement and concrete are carbon intensive, and what we can do to fight the conservatism that's built within our current codes, our current specs, our current standards that really prohibit us from making some of the change that we need to. And I will tell you, we've made some good changes. I'm going to talk about things now, but idea here is don't be sad. There's a lot of opportunity here to innovate, and we have a lot of help with people interested in helping us as a species change our behavior. So why the focus on cement and concrete? I'm sure, again, most of you have seen this. The reality is, for every man, woman, and child on this planet, we produce about 2.2 cubic yards of concrete per year. All right, we love concrete. Concrete's a wonderful material. Civilization, as we know it, is built with concrete. And that's not an exaggeration. You wouldn't have running water when you flush the toilet where it's going, buildings, everything. Concrete's wonderful. But because it's used so much and it is so robust and so easy to use and forgiving, it's roughly responsible for 5 to 8% of the CO2, the greenhouse gases that we generate in the world. The numbers in the US are smaller as a percent of our economy. We roughly manufacture 90 million metric tons of cement in the US in 2020 versus the 4.1 billion metric tons manufactured worldwide. And that's about 0.6, 0.7% of the US greenhouse gases. So it's a smaller percentage, but that doesn't mean it's not significant and that we are not the focal point of those that want to lower our carbon footprint. Where's it coming from? If I look at concrete in a ready-mix truck at the gate, all right, it's leaving the ready-mix facility. 1.5% of the CO2 in that cubic or that 10 cubic yards of concrete is basically from acquiring and processing the raw materials to make that concrete. 89% is from making the Portland cement. 9.5% is wrapped up in actually making the concrete, the aggregates and whatnot. Out of that, which is from the 89% from the manufacturing, 37% of all the CO2 involved in that concrete in that truck is from the fuel burning in that kiln right there. And if you haven't seen a cement kiln and you have an opportunity, take it. It's an amazing thing. It'll scare the bejeebers out of you. You know, I mean, the heat is incredible, right? Around what, 27 degrees Fahrenheit is what they're, I think, isn't it around 2,700? So it's hot. You know, that's probably where Jimmy Hoffa ended up, you know, in cement clinker. But 46%, almost half of the CO2 in that truck is from taking limestone, calcium carbonate, calcining it, and driving off CO2. All right? The chemical reactions necessary is to create Portland cement. And that's really tough to get away from, right? No matter what efficiency we bring into our whole system, that truth stands. That truth stands. So net result is for about every pound of cement, kilogram, metric ton, take your measure, that we make in the US, roughly 0.922 pounds, kilograms, metric tons of CO2 is generated. A little bit less than one. When we look at, again, concrete, typical concrete at the gate, the number here is about 0.26 tons of CO2 per cubic yard. That's kind of an average number. It can be higher or lower. And roughly 0.23 tons of that is from the Portland cement in that concrete. So guess where the focal point is? If you're going to deal with this problem, what are you dealing with? Portland cement, right? And how many cement manufacturers I have here? Are these numbers about right? Now, these are our numbers. And as you as a manufacturer, you know this is what you got to do. And so what are we going to do? Net zero 2050. Again, the PCA is supporting this. There's a big commitment on the part of the Portland Cement Association. They have a really nice roadmap. You can read it. I'm not going to talk about a lot of it, but they go into clinker optimization and sequestration, optimizing their cements that they're selling, optimizing concrete, in-service end-of-life carbonation. I'm really going to drill down really on two things right now, primarily due to time and the focal point of what we're dealing with here. And that is, what can we do right now where you're sitting when you're making any concrete and concrete for airports? One, replace clinker with supplementary cementitious materials. That's the simplest thing, right? So we have a 6-sack mix in our concrete, 564 pounds per cubic yard. We're going to replace 20% of that with fly ash. That's a big savings right there. We're going to maybe do 25% or 30%, or we're going to go further. We're going to go in and we're going to now blend some limestone in there, right? An ASTM C595 type 1L. How many of you are seeing that in your markets right now? Pretty much all of you, right? That's been brewing for like 12, 13, 14 years in the States. Colorado's been using it since like 2008 in paving. And all of a sudden, within a year, everywhere we look, PLC. That can have up to 15%. Really, it's usually 12, 13%. We take that and blend it with an SCM, and we get further reduction. And the chemistry here is such, and the particle packing is you actually, with an SCM, with some illuminates, with that ground limestone, you get some benefit that's actually better than the SCM would do without the limestone. So there's a lot of ongoing work right now. People are looking at even higher contents, up to 25%, not for paving. I wouldn't recommend that, but if I'm doing a masonry block or something of that type, it might be perfectly acceptable. And so from a cement manufacturer's perspective, they're under pressure to reduce their carbon footprint. They are going to want to provide blended product. And as things get more complicated, it's going to be important because there's a lot of chemistry involved here that most of us as civil engineers hate. That's why we're civil engineers and not chemical engineers. But you got to balance things out, like your sulfates and all of this, for getting the right hydration mechanics. And as things get more complicated, let them do it, because when it goes wrong, then you know who to sue. You sue them, not the ready-mix supplier who put the ash in. Lots of good sessions already. We all know about fly ash. We all know there's shortages of fly ash, right? Why is there shortages of fly ash? Because we're trying to burn a little less coal. But there's lots of fly ash that's in landfills. So we're harvesting that. And a lot of good papers on commingled fly ash with bottom ash. And now we talk about coal ash. Larry's back there. He's very active at ASTM, and they are working diligently to try to make sure that our specifications grow to not provide limitations, that we keep using quality SCMs, coal combustion products in our concrete. So we want to make sure we have those. Slag cement can be used. Natural pozzolans are of immense interest. And in some places in the country, there's great supplies of these. Other places are going to be, cements are going to be manufactured with, maybe 40% clinker, 50% clinker, a high percentage of limestone with then calcined clay in a whole new system called LC3 or LC2. Again, this is later in life, like maybe next year. But it's important to recognize that we have solutions. These are different than what you are used to, but they are things that we will be doing, and you will develop knowledge on how to do it. As I said, the real push is in this idea of using the blended cements, the 595s. They can be a 1P, which is a pozzolan blended with pozzolan, a 1S blended with slag cement, a 1L, which is blended with limestone, or a 1T, which is blended with two of those. It could be a limestone with a pozzolan, limestone with a slag, two pozzolans of that type. Typically just the 1L, depends on who you talk to, but it might reduce your carbon footprint 7 to 9%, 8 to 10%. So it's an immediate reduction. And it's designed to be fairly seamless. And how many of you are like ready mix producers or contractors? Anybody here? Have you worked with the 1Ls? How does it work for you, honestly? And how has it been for you, man?
I'm in stabilization, so we're not ready.
Okay. Yeah. I mean, the idea is most contractors, ready mix suppliers will say, some will say it's a little this, a little of that, but you know what? If I go from one type 1 to another type 1, I get the same kind of fluctuation. So the 1Ls are designed to be pretty easy, should integrate right into your system. And that's why the transition's underway. And you can, all of these questions have been answered with sulfate resistance and heat. And if you look in the short time in these two charts here, geez, I can't even, what does that say on the top one? What year is that? 2018 to 2022, the amount of transition was so fast. No one saw that coming, that the transition to type 1Ls is going to be as quick as it's been. So this is a real success story and a map to help us move forward. The second part of this is let's put less cement in our concrete. All right. So that's the second part. Less clinker in our cement, less cement in the concrete. Very easy to do. This is already allowed, completely allowable and encouraged within the P501 spec for airports. This is Tyler's curve, or at least Tyler and company. He's worked with a lot of people over the years to develop this, a lot of mixes. This is the curve that for airports might not work as well, from standing up the edges and not getting some sloughing of the edges. And so that's going to be investigated because Tyler just got a contract last week to deal with this. I'm lucky enough to be on the team along with Dr. Smith over here. So we should have a good time. But the bottom line here is there are tools available to take your aggregates. And if you're working with concrete, you should not be thinking of it as coarse and fine aggregate. You should be thinking of the blend of the aggregates and filling space with as much aggregate as we can and getting good workability, getting the workability that we need, and yet minimizing the need for paste. And so when we approach it this way, we can reduce our paste quite a bit and fight a common fallacy. And the fallacy is that somehow more cement, more cementitious materials equals more strength. That is not true. Now, it can give you higher early strength because the heat of hydration will kick it off a little bit more. And that is of value in construction, right? We don't, if you're a contractor, you want to be able to strip forms often as early as you can. Or when you're slipping a pavement, sometimes you want to be able to use that for an access road. But on airports, sometimes you're not under the same time constraints. And so you have a little bit more time. But the bottom line is this is some work that Peter did with one of his grad students that just showed that at different days, that once you get beyond a certain cement content, there's no change. I showed this one because this is a real project I worked on. This is Project Neon, Interstate Highway, I-15 through Vegas. We had a 500 pounds per cubic yard mix that got approved by the DOT through an ATC, another nice acronym. Nevada, the minimum cement content requirement in Nevada to this day is 611 pounds per cubic yard. That's their minimum. We got them to accept 500 for this project. This is strength data from 3-day averages. And we switched as we got into summer because what happened is this was 100% manufactured sand. And that mix started under the heat and a little bit of moisture control issues, I'll say, with the ready mix supplier. They were getting a little stiffening of the mix. So then the only other mix they had approved was the 611. But if you look at this data, even at 3 days, there's not a lot of difference, right? Factoring in the fact that this stuff was February, which even in Vegas is cold compared to later. If you look at the 28-day averages, we actually had, on average, higher strengths with 500 pounds per cubic yard than we had with the 611. And so this can be done and it should be done, especially on airfields. And so the general trend here, the way to think about it is basically go away from your pure Portland mixes, reduce your cement contents, and then basically, reduce your cement content, same time, try to replace clinker with SCMs. If you look at the current P501, it actually allows you to do a lot of things. You know, that it does not allow 1Ts, but it does allow all of the other blended cements, including 1Ls. The military does not allow 1L at this point, I don't believe. That's what Peter was talking about. They're the ones still having heartburn. Last ones. Basically, you can, they have their fly ash specs, but they encourage the use of fly ash from 20 to 30% replacement. And unless used with slag cement, then 10% max. You can use up to 55% slag cement. And they allow you to go as low as 470 pounds per cubic yard, unless in a freeze area where they say 517, but you could actually go, they'll let you go lower if you petition them. I will say, I thought I added it, I don't see it here, but the idea is, one limitation is they don't allow you to use superplasticizer. So for some reason, FAA does not allow the use of a type F. So I'm going to go try to finish quickly. I'm watching my time here. I think I'm okay. I got 3 minutes left and then I'll 5 minutes for questions. Because 5 minutes is not enough, but questions are good. So keep that in mind. Assessing what we do is critical to moving forward in the right direction, because all of you know there are pressures for all kinds of easy levers to pull. So what we want to do is we want to do these easy things, and we want to track ourselves. And the best way to ultimately do it is going to be using either EPDs that are based on life cycle assessment that are done according to standards. And I don't have a lot of time to cover this, but I want to mention it because this is where the industry is going. If you have not been asked to this point to provide an EPD for your concrete, you will be. And that's not that far in the future. And so EPDs, there is a document that was produced through the Sustainable Pavements Program that was led by, again, Dr. Smith here. And I don't think either one of us worked on this document much. You probably did, but I didn't. But this is a good document. It's from the Federal Highways. You can download it, give you some good background. Basically, these will communicate the potential. This is creating more or less a nutrition label of all of, over multiple environmental impact categories for your product. And in the end, you start with a set of product category rules that are developed through a very rigorous open process. From those rules, once they're established, you will then be able to analyze your concrete product, and from that, generate an EPD that gets filed with somebody like ASTM, and then it's available to show where you're at. And as you make changes, you can show improvement. And it looks like something like this, and this is a real EPD from Central Concrete in San Jose, California. But many ready-mix producers are now producing these, and you can get this information, and then you can track your decisions and how they are affecting your greenhouse gases. Last thing I'm going to talk about is just some work that I'm involved with Larry with right now at Minroad. It's not an airport project again, but we're actually designing right now a test site with 16 test cells that are going to look at various carbon reduction strategies. And so we're going to have a control section. We're going to let Dr. Taylor here optimize a concrete mix to reduce it from their standard 6-sack mix down to whatever he can pull out of his lab. There's going to be 3 carbon mineralization sites. And then there's going to be, we don't really know the combination yet, but alternative SCMs and alternative cementitious systems, alkali activated systems. We're hoping to get some geopolymers in there, but they all seem like they don't want to go through a ready mix plant and get paved with a paver at this point. You know, that's the deal. It has to go through a standard ready mix plant and get placed with a paver. And so that work is going on, and we'll be able to talk about that more in the future. But I think the bottom line is, yes, we are entering a challenging time. It's going to be an interesting time. I've used 25 minutes. That's not bad. The main thing that I would want you to walk away with is don't be depressed about it. We have a bright future, and make sure don't let all of the acronym soup of developing an EPD scare you to death. Figure out how to do it and use these to avoid greenwashing, because the greenwashing is what I really feel could do us a lot of harm, because we're going to get, eventually we're going to find out we've been wasting our time and we're going to feel pretty ripped off. So I think we got a bright future.